start? Well, hello. Today I will talk about cloud-optimized HDF5 files. So last month I talked about something kind of completely new, an idea of HDF implemented as a bunch of objects in an object store. Today we're talking about good old HDF5 files and how to make them cloud optimized. And the concept of cloud optimized files I became aware of is about, I would say, 5 years ago, when one flavor of the TIFF file format, TIFF is a tagged image file format, that flavor is used widely in commercial remote sensing, satellite or airplane or photogrammetry. It's called GeoTIFF. So they came out about 5 years ago, and they said that they proposed a version of the GeoTIFF file format that is cloud optimized, and it created a huge impact. Was very popular. It's still very popular. It's almost now the norm to see GeoTIFFs as cloud optimized because a lot of that kind of processing moved into cloud. And so I said, well, let's see what HDF5 can do in terms of having cloud optimized HDF5 files. And that's what I'm going to talk about today. I'm not claiming this is the only way. HDF5 library has, depends what your angle is, a lot or plenty of options that you can tweak how the files are created. So maybe there is other approaches that will achieve the same result, but this is the one that I kind of so far examined, and I'm going to talk about it. Now I have a presentation for today. It's not that I made it for this, but I'll be talking about this month twice, and so I thought I probably should prepare slides for it. So let me see how I can share this without ruining. So let me see if I can start presentation and then share the presentation. That's at all possible. Maybe not. Let's see. And as I'm doing that, I will say a few words about the sponsor of this work. I hope you see it. And I hope that now it's going to be better when I do the presentation mode, hopefully.
Yep.
Do you see? Okay, excellent. Wow, that worked. So the sponsor of my work is the NASA Earth Observing System Data and Information System. They are big users of HDF5 files. I mean, producing them and obviously using them. And they are now, about the last 3-4 years, they made huge efforts to move into the cloud native distribution and processing of Earth science data. And so they're very interested to, on all this topic, how to make HDF5 files more accessible and more performant in a cloud native way. And specifically, this is under subcontract from Raytheon Technologies, and the contract number is there somewhere at the bottom. So, legally obliged to mention it. But other than that, this was really a huge support of HDF Group. And so I'm very glad that they continue to do so. And I hope that, people appreciate how much from their support came to be shared by the wide community. So, so what is cloud optimized storage format? Just to clarify what I mean. And so this is what I came up with. It's already existing file format where internal structures are rearranged for more efficient data access when in cloud object storage. There is also something I call let's see how I can move. Okay, there is something called cloud native storage format. And the difference is that this is a specifically developed data format to take advantage of the key value interface of distributed, you can read it, and the key value interface of the object storage system. And by definition, anything cloud native is also cloud optimized, obviously. And so how cloud native differs from cloud optimized? Well, in cloud native, most of the cloud native, or exclusively all cloud native formats that I've seen, essentially have one file, what we would call a file, contains of many objects in Cloud Object Store. That arrangement allows for modifications, because now you can modify objects of the file. And obviously data reads so far mostly access the entire object, although it is possible to go within an object, but mostly conventionally entire objects are read or obviously replaced if they're modified. For the cloud optimized, you have a more traditional conventional situation. There is a file, and that file was somehow copied into an object store. And because of that, there's only read-only access, and any update actually has to include overwriting the entire object. In other words, replacing that file in the object store with a new version. And the mechanism how data is accessed is through this functionality called HTTP range GET request. Not all web servers support it, but most do. And that means that once you request some bytes from an object via HTTP GET request, you can actually say which range of bytes should be read from. And that really is a big, big help. This also means that you don't have to really be in a cloud object store. You could actually have a traditional, conventional web server, Apache, HTTP, or whatever is now the latest, NGINX, and configure it to support the range GET request. And you could have your little cloud object store there supporting exactly the same type of access. So I'm not going to talk about that. We are, don't have enough time for all of these things. But basically, my point is that if there is a need for these HDF5 files to eventually find their way into cloud object storage, then probably would be good to think about producing them as cloud optimized files to begin with, to reduce the amount of reformatting needed, because usually scientific data is in HDF5 files, and scientists really don't like when their data is being in any way or form reformatted. And so I think it's a benefit to reduce that. Also, in a lot of methods that bypass or don't use HDF5 library for access to HDF5 data, there is one very important first step that's required, and that's to scan and know what's in the file. And if that's not done prior to the file leaving a local file system, and that has to be done when the file is already in the cloud object store, then that step can be very, very slow. And also, last, which I think is kind of important, is that HDF5 library can read HDF5 file format very effectively, obviously. And so instead of developing your limited features custom data reader, which is great because it says the HDF5 format is accessible and open source and all that good stuff, but you still don't have time usually to develop a reader for all the features, then why use it? Better to use HDF5 library. And I think with cloud optimized HDF5 files, the library can achieve very satisfactory performance in terms of some tests. I'm not going to say for every test, it's still to be determined, but for some tests, it's quite good. So I cannot see the chat if anyone asks questions, or if anyone wants to ask questions, ask while I'm talking better, then wait for the end. So what are the properties? Here's the big slide. So the most important feature is that they have to be created with paged aggregation as the file space management strategy. That's not the default of the HDF5 library. The other thing is that large dataset chunk sizes, and by chunk sizes I mean the size in bytes, not chunk shape, which will be the number of elements along each dimension. I'm talking about chunk sizes as bytes. So that's second one. Obviously, the third one, for large chunk sizes, the compression algorithm probably has to make some kind of compromise between a almost maximum compression versus the speed to decompress the data. And fourth one is also kind of interesting and important, to basically avoid, if possible, or really minimize the use of variable length data types. I'll mention why is that. Especially important, obviously, if HDF5 library is not going to be used to access that file. So, variable length data types. The way how their variable length data is stored in HDF5 files prevents it easy retrieval with this range get request. And that's the main reason why I'm suggesting to be avoided altogether or really minimally used. Because if someone is going to use an alternative method for accessing HDF5 data, they will have to essentially store variable length data in some other way outside of the file, which is not optimal, obviously. And so the least amount of variable length data is the better. Luckily for NASA and this Earth observing system applications, they don't have a lot of variable length data. They are, numerical kind of data. But I see possibility, especially with these AI ML training data sets that use a lot of labels and categories that are strings, then they may just use variable length strings just because it's available, but that could maybe create this kind of issues. Large data set chunks, yes. So essentially, the issue with data accessing cloud object store is that it's an HTTP request, and it takes a lot of time compared to, for example, local file system. I mean, if we talk about S3, I think my experience was anywhere between 50 milliseconds to 170 milliseconds for each request to sort of be completed. And so that's a lot of time. And so if you're going to request data, better to request more than less, because going back and forth is not really advisable. And so large data set chunk sizes are really going that direction. Amazon Web Services have this best practices paper. I maybe published about 3, maybe even 4 years now, where they kind of suggest that one range get request should be roughly about 8 to 16 megabytes. I have nothing to argue against that. They probably know more, but I would say I've seen cases where chunk sizes went into a 100 megabytes. Although given those are the applications that needed to apply a lot of statistical aggregation functions on the data. And so probably for them, it was easier to have in memory and just run these things. So 100 megabytes was acceptable, but I don't really think that that's justifiable for any kind of data. And obviously, once someone decides on the chunk size, it's easy to work back what should be the chunk shape that fits into that chunk size. And if you start having multiple megabytes in a single chunk, then obviously all these problems with the appropriate chunk shapes for the data access patterns, it's kind of not anymore as maybe important as it used to be, or as is when your chunk is 50 kilobytes. You're probably going to have a lot more data in a couple of megabytes chunk. And so really getting the chunk shape correctly for your data access may not be that important now. But again, I'm not going to make huge claims that that's now solved problem. Who knows? I think practice always reveals various strange things. All right, that's just repeating things. One thing that I want to mention that I also found out that people are not always aware of is that HDF5 library actually has a chunk cache for every HDF5 dataset. And for some reason, HDF5 library, even in the 2023, comes out with that chunk cache being only 1 megabyte. And so you just know that you can increase it and configure it per dataset. So if people really want to increase their access to vary number of chunks, then this is the place where they have to increase the chunk cache. So that's something I just want to mention as a side note. So we can continue next. Yes, so this paged aggregation, that's a big thing. It's one of these file space management strategies that's available. I think I noticed that it's been added since 1.10.1 version of the HDF5 library, but don't quote me on that. But certainly it's been around. It's not brand new. It has to be set obviously only at file creation. So for all these files that currently exist, it's kind of too late now. So there are other ways to make them cloud optimized. But for any new file, this is the way to go because it must be set at file creation. And also, it is really best suited to files where with the content just being written out and never modified. And that is in the communities that I tend to participate in, that mostly is the workflow, that these files are written out once, they contain some data, that data in that file is just a part of a much longer, bigger data set, bigger collection of files that have some meaning. And so it's very rarely that these files will have some longer life being modified or something like that. They're written out, shipped, and that's it. So I think in those kind of cases, this page aggregation is really helpful. And so I'm not going to go into this thing. This is take too much time. But here is the main idea, what makes these files cloud optimized. That if a person set a appropriate file space page size, then there is a potential that entire internal file metadata gets into very few of these pages. And getting this information in the very few file pages is very critical for the good performance in Cloud Object Store, because then it will require only a few requests for these file pages to get all the information what's in the file. And that is critical for Cloud Optimized file format. Essentially, and I forgot to mention, in Cloud Optimized access is very essentially simple. Make as few requests for data as possible. Out of those few requests, make even less for what is where in the file, preferably only one. And everything else you make for the data in that file, and hopefully parallelize those requests. And that's pretty much the whole theory of Cloud Optimized data access. So that's why this page aggregation can help here, because it forces the library to write out the internal file metadata information, what is where in the file, in a very few file pages. And so how to apply page aggregation? So as I said, for the existing files, sort of the train left the station, so you have to use H5 Repack. And it has the capital S and capital G command line options, and basically -S page is required. It tells we're going to use page aggregation, and then capital G with page size bytes is the important parameter, and then input HDF5 file and then output HDF5 file. For the new files, there are these two APIs, on the file creation property list, where you set your file space strategy and then set the file space page size. And obviously then off you go with all the other things. So one benefit of using paged aggregation is that the HDF5 library now allows the use of page buffering, which is another cache available by the HDF5 library, but is only available if the file is created with paged aggregation. And page buffering now caches these pages even before they become dataset chunks or something else. But they're cached. So there's another low-level cache that people can use to optimize their data access. And the good thing is the library actually provides statistics about access to the page buffer. And so people can look at it and optimize the size of the page buffer and everything else. The only thing to know about is that the page buffer size has to be an exact size of the file page size. And there is a chicken and egg problem here, because if I don't open the file, I cannot find out what was its file page space size. So that's the one thing I have not really worked out the best approach, but you would have to open a file, learn about its file page size, then close it, then open it again, now specifying the page buffer. So there may be an optimization thing in the HDF5 library in the future, but so for now, this is the only way I'm aware of how to do it. So case study. I used an HDF5 file from a satellite that NASA has called ISAT-2. And this satellite has 6 laser beams that are constantly shooting pulses to looking down. And it's kind of being used to measure ice sheet thickness or vegetation height, many other things. Essentially anything that can bounce the laser light back to the satellite, this instrument picks up. And so I just use this case because these files have a lot of data, a lot of content in the file, and they're known to be a pain to access in the Cloud Object Store. And so I said, well, let's see how we can do with this kind of thing. So this particular file has about 2.3 gigabytes in size. It has 171 HDF5 groups and 1001 HDF5 data. But here is the important value. This HDF5 file metadata size is 7.7 megabytes. And this is an important number to remember. So what I did, I actually used H5 Repack and used 2 file page sizes and paged aggregation. So I used 4 megabytes, or megabytes, sorry, and 8 megabytes. So essentially what I did is I stored the internal file metadata in 1 or 2 pages. And then we try to access and do something with this new file and see the performance. So how to find internal file metadata? There is this tool called H5 Stat, and it's option capital S. And basically, when you call it on this file, for example, it prints out all the information. And here, as I said, file metadata. This is the important number. So let's see. I saw something that participants can now see my application. Was there a problem before that I was not aware, or no problem? Anyone can talk?
No problem.
All right, thank you. All right, so you call H5 Stat and you find what's your file metadata, and based on that you decide how much your page size to be. And so if you see 2 lines above, file space page size on this current traditionally created file by NASA scientists, you see it's only 4 kilobytes. And therein lies the biggest problem. Why, if you put this original file into Cloud Object Store and then have HDF5 library or anything like that actually going to do something with this file, poor thing will have to basically request a lot of these 4 kilobytes from the file to figure out what to where. And that just basically kills any performance. And so, case study. So I put the original file and these two Repack version in S3 bucket. And then I use this common test that I say for many applications that bypass HDF5 library need to do. And that's essentially quick scan. Well, not quick, but they have to scan the file and learn what's where in the file. And that what's where includes the groups, the data sets, their attributes and their values, and also chunks and their chunk location and their sizes. Because what they need to do is actually they need to read the chunks from the file using HTTP range GET request. And so all that information is in the internal file metadata. And I just mentioned some of these applications that people in geosciences are more familiar with, but don't worry about that. So while I was testing, I actually tested with H5Py 3.7, but it was custom modified by me to actually have some things that are not available, that were not available at that time in H5Py, but now they're available because I bring them into the H5Py. They're now, it's not still officially released, but it's in the master branch of the H5Py repository. And I use H5Py 1.13.1, but good news, currently recently released 1.14.0 also works, and I checked it. I just didn't update this slide. And I used H5Py and HDF5 library with two ways. I was using the library's own, its own S3 virtual file driver, but I also used a Python package called S3FS, which provides file system access to S3 bucket. And there is an interface in H5Py that you could actually plug in any Python object that looks like a file, and HDF5 library can use it for source of reading or writing. So I try to use both of them. S3FS, I have to say, is is better if you're a serious S3 user because it has all the fancy ways that you can authenticate and has a more features by itself. The read-only S3 virtual driver that comes with the library is useful because it's so basic and simple that if there is a huge improvement in performance, there is no doubt that that's because of this paged aggregation and other optimization in the file. So it's useful as an indicator. So computing environment, I use the M5X large in EC2, all in the same region because no one wants to pay cost of data crossing the regions or stuff like that. And I use Python 3.11, I mentioned that. And so I compared essentially, that's actually more updated slide. I probably have to remove that line from there. So yeah, so I explained it. Anyway, so first, how am I doing? Okay, not bad. So first was the timing, like how much time it takes to repack the already existing file with different page sizes. And I used even more page sizes than I actually used in my other tests, but I just wanted to see the time it takes and how much the files actually increase. Because now with these new file page sizes, actually the library has, because of the file page size, there is empty space at the end of each page. So I just want to know how much is the file increase. And as you look, the time is always around 19, 20 seconds, so it's not bad. And the file increases are quite acceptable, especially if you're talking about several gigabyte files. This is really acceptable. At 32 and 64, obviously things start getting bigger. And why I thought about 32 and 64 megabyte page sizes is because I thought about how many chunks would go into one page. Obviously, having more chunks in a page is better, but where is that optimal threshold? Then it's questionable. So that's why I went even bigger than right now. So here's the performance result. So what I did is I used these three versions of the files, and this is sort of a baseline. So all these files are in the local file system, which was EBS volume or EC2 instance. This is where the HDF5 library is in its natural environment. So let's see how it performs. And and I used the original file, and I did this listing of the file content, or the chunks, locations, the whole thing. And I computed, I don't know how many times I ran it, but this is a statistical number. It's not just a single run. And anyway, I assume that's 1. So any number bigger than 1 means that it's kind of slower. Any number below 1 means it's faster. And so I used all these files with 4 MB and 8 MB page sizes, and I used page buffer of 4 MB, 8 MB. And then I measure them. And obviously there is a very slight degradation in performance, but it's kind of understandable, especially in the case of the 4 MB page buffer, because in this case, the library has to sort of throw out one page with internal file metadata to get the other one and then go back and forth. So it's a lot of throwing out of things in cache, in the page buffer cache. But I would say it's not bad. When we moved to S3 using the HDF5 library, using the HDF5 library with its own S3 VFD, if you put the original file, it's 17 times worse than when that same file is in the local file system. However, when we start now using these paged aggregated versions, with different page buffer sizes, now we start getting a little more. This one is only 6 times worse. But now when we essentially have page buffer of sufficient size to hold entire file metadata immediately, we're now starting to get very comparable results to this baseline case. And I think that's, for example, indication of sort of this cloud optimized performance. Did someone trying to say something, or? All right. And the other one is now with this S3FS Python package. And unfortunately for us, S3FS has its own caching capabilities that kind of complicate things. And I'm not going to go into details what they mean, but S3FS, for example, has a minimum amount of data it will request, and its default is 5 MB. So in cases where we're dealing with the original file, it's even worse because it's requesting 5 MB always, regardless of how much actually it needs. So the performance is even worse than the library's S3 VFD. But again, when you start playing with these things and you actually start doing this cached, this page aggregated versions of the files, the performance here starts going slightly below 1. And when I looked into the logging of S3FS, I think I figured out that the key to that is because it can do asynchronous requests. So essentially, as soon as there are more than one request, it makes a synchronous request by itself. And maybe that was a little, maybe gave a better little performance than the library. But again, this is all very close to 1. So I'd say essentially it's exactly the same if the file is in the local file system or it's in the object store. But again, it has to be cloud-optimized HDF5 file. And that's basically all. Yes, this is also some wrap-up, but basically, I already told you all of these things, so we can skip it. And yes, there you go. Thank you very much, and I'm going to stop sharing. So, any questions? Now is the time.
Great stuff. I got to run in a moment. I had one comment, if you want to. On your slide 11, I think you had a bullet where you said paged aggregation works best with sort of write once and read many. And I think that's true in some abstract sense, but I think one of the features that we also introduced in one of the 110 releases, and it might have been in 110.1, you can actually turn on free space tracking, where you, beyond a file open, file close cycle, you keep track of, you can set a threshold to keep track of free space in the file. And so if you create a gap somewhere that's greater than the threshold, it will be tracked in the file metadata. And later, if there is an opportunity to fit an allocation in there, the library will do that. But so I'm not fundamentally disagreeing with you. I'm just saying, yeah, it certainly, I mean, most things work just fine for write once, read many. But yeah, we also, there was quite a bit of work in free space management.
Yeah, I mean, I remember I've seen something to that effect, but I made this for the audience, in which for them, they never come back to this file unless they reprocess the data, and then these files are completely a new version of the file. They don't go and modify a few things there. So, but yeah, the other thing that I didn't examine yet, there's still months in this contract. So what I didn't examine is, now that I'm getting these chunks in one page, I didn't look, are these chunks for the same data set, or they are sort of just thrown in together for various data sets? Are they nicely aligned or not? Because I'm aware of some applications that do super chunking. So they try to figure out how many chunks are kind of close next to each other in the file, and then basically say, well, when we're going to request, we need 3 out of 5 of this here, so let's request 5 and keep them there rather than going for each one of them. So I have not made sure to see how these chunks are aligned after repacking or something, but that's maybe something to look at. Although I acknowledge that really depends also how the files are created. And I know that, again, in these cases, they're very orderly created. They create a data set, write out the data, create a data set, write out the data. There is not a lot of chaos when the data goes out to these files. So yeah, that's all I have.
Good stuff.
Do
you plan on doing any HSDS comparisons? I mean, not to say one is bad or the other is good, but just to understand what kind of HSDS configuration, well, what is the HSDS performance out of the box, so to speak, but then also how much does it take to get to that performance level? What do I have to change in my HSDS configuration?
Yes, so one thing that I also didn't do in this study was, because there were so many data sets, I didn't re-chunk them. And doing H5 repack and basically specifying how to re-chunk 1,000 data sets is kind of painful. And so that would be another thing to study, because HSDS would definitely benefit from having faster scanning of the file content, but the HS load and HSDS also re-chunk, and so that's something to be aware of. In this case, these files that I did, they didn't have any. They had original chunk size that was not changed at all. So yeah, I mean, we can look at, obviously.
Because in HSDS also, you would have 2 options. You could import the HDF5 file just as a blob, and then you should actually get the same benefit because you are using the HDF5 library to access that blob. But no, you don't.
No, you don't. No.
Yeah. But then, so you can basically deal with the HDF5 file as blob, but then also re-chunked, as you just said, going through HS load. Yeah.
So that's all. There are ways to play with this, obviously, and to look into these things. But hopefully there will be more time to to examine other aspects. But again, for a lot of cases, this one that you scan and you get very quickly, it's a very important step. And we'll see how, I mean, obviously, we'll see how his intake happens and what people report afterwards. Whether or not having chunks in these file space pages are useful or not, and how much is that useful, obviously, if you end up having chunks that you don't care about in your file space page. I mean, this is all, but there are so many different scenarios that it's really difficult for me to say, well, we tried something and we are fairly certain that there aren't going to be any problems or issues. But obviously, page buffering, make it, 1 gigabyte. What's the problem? How many gigabytes we now have on our laptops? Why not make a 1 gigabyte page buffer, load up your chunks there, and see what happens? I mean, why be? There is no need to be frugal. So anyway, that's
Alex,
all I have.
I had a question. Was curious what you felt the performance was relative to the overall max bandwidth from your EC2 node. M5 extra large is like up to 10 gigabits, right?
Yeah. Yeah.
How much of that did you fill? What was your percentage?
I have not monitored that.
Well, okay. Is it possible to back solve what the megabytes per second IO looked like?
I could actually, I mean, there is logging, at least for this S3FS, who could tell me how much bytes were requested and when it arrived. So you could probably look into that and work backwards. What was happening 5 years ago, I did a study that I actually had S3 logging enabled. So we looked very low level S3 logs to work out exactly these kind of things that you're talking about.
Well, I was just thinking the big picture performance, when you gather data. Oh, I got the wrong camera. Anyway,
okay.
I see that it's working, right? But maybe I missed the slide that showed how fast this goes, right? What was the performance you were actually just seeing?
I didn't do bandwidth at all. I just did how much time it took to complete this task because I had.
Okay. Well, how much data were you moving? Maybe we could do it on the fly.
Yes. I have not measured how much data was moved.
Okay. Yeah.
No.
How efficient it is on
network
bandwidth,
Yeah, absolutely. I went all the way to the end user, the person who just wants to scan and say how long is going to take me to get this information. So I was more geared towards them. But yeah, I mean, there are many ways you can try to follow what's going on. But yeah, I would like if people want to jump in and try these things and report various angles. More info, more eyes on this thing are usually always better.
Okay, well, it's just similar to the vol connector that the AWS kind of cloud native vol connector that I described at supercomputing in November, right?
Yeah.
Because running on the EC2 instance, doing IO directly to the S3 objects, range gets and multi-part puts, all that. So was just, I'm getting kind of.
It'd be nice. It would be nice to play with that as well. So, but yeah, again, as always, this is always open to anyone to examine, contribute, discuss. We can always revisit this thing.
Okay. Yeah.
Well, all right. Thanks, Chris.
I might ping you back then.
No problem. All right. I have another meeting starting right now. So thanks for showing up. Unless any more questions, I will leave the meeting to join the other one.
Oh, so, thanks, Aleksandar.
No, you're welcome. Take care.
Bye-bye.